Hi everyone, in this video we're gonna talk about one of the applications of differentiation, which is applied maximum and minimum problems. Our group name is Triangular Trio and we are from CTCS 143. Introducing our group members, Nur Aina Ayuni, Alicia Irjina, and Nur Azwaniza Fitri.
What is differentiation? Differentiation is the process of finding the derivative of a function. The derivative represents the rate of change of the function with respect to its independent variable. The result of differentiation is called as f prime x or dy dx or y prime. In simpler terms, differentiation allows us to understand how a function changes and is widely used to analyze rates, optimize functions, and study motion. There are 5 applications of differentiation, which is the first one is related rates. The second one is analysis of functions 1, which include increasing and decreasing functions and concavity. The third one is analysis of function 2, which include relative extrema, first and second derivative tests, graph of polynomial and rational functions. The fourth one is applied maximum and minimum problems. And the last one is Rolle's theorem and mean value theorem.
What is applied maximum and minimum problems? The process of finding maximum or minimum values is called optimization. There are many application problems to solve real-world involved function to find maximum or minimum values. For example, maximize or minimize cost, profit, area, volume, or time. So now, we move to the question how to solve the applied maximum and minimum problems. Firstly, find the first derivative. Next, let the derivative equals to 0 and find the values of variable by using function. Lastly, find the second derivative to determine the value whether minimum or maximum value. If the second derivative more than 0, then the value is a minimum value. But if the second derivative less than 0, then the value is a maximum value.
A company wants to design a rectangular box with a square base and an open top. The box must have a volume of 2000 cm3 and the cost of the material for the base is Rm 5 ringgit per centimeter square, while the material for the sides costs Rm 2 ringgit per centimeter square. The first question is A. Show that the cost of the material is C equal to 5x squared plus 16,000 over x. First, we know that the box has a square base of the side x, so the area of the base is x squared. And for the side, since the box has 4 vertical sides, each side has an area of x times x, which is the total area of the sides is 4xh. So now, to find the cost of the material, we need to sum the cost of the base and the cost of the sides. The cost of the base is calculated using the area of the base, which is x squared multiplied by Rm 5 ringgit, and the cost of the base would be 5x squared. And the cost of the sides is calculated using the area of the side, which is 4xh multiplied by Rm 2 ringgit. And the cost of the side would be 8xh. So the equation would be cost equal to 5x squared plus 8xh. Now, given the volume equal to 2000 cm3, which is x squared h equal to 2000. So to find the h in terms of x, we rearrange the equation and we get h equal to 2000 over x squared. Next, substitute the value of h into the cost formula. which is cos equal to 5x squared plus 8x in bracket 2000 over x squared. So simplify, and the equation we get 5x squared plus 16,000 over x. B. Find the dimensions of the box that will minimize the total material cost. For step 1, find the derivative by differentiate equation of the cost, which is get dc over dx equal to 10x minus 16,000 over x squared. For step 2, let the derivative equal to 0, which is let 10x minus 16,000 over x squared equal to 0. Next, solve for x, which is 10x equal to 16,000 over x squared. And then multiply both sides by x squared to eliminate the denominator, so that the equation will get 10x cubed equal to 16,000. Now, divide both sides by 10 and the equation will get x cubed equal to 1,600. Finally, take the cube root of both sides and using the calculator, and we find that x equal to 11.7 cm. Step 3, we need to do a second derivative test by using dc over dx equation. So we differentiate the equation to get d prime c over dx, and we get 10 plus 32,000 over x cubed. By using this equation, we can substitute value of x, which is 11.70, into this equation, and the answer we get 29.98. As we know, if the value is greater than 0, then the answer will be minimum value. Since our answer is 29.98 is greater than 0, so value of x equal to 11.70 is a minimum value. Next, to find h, which is side length of the box, we can substitute the value of x into h equation, which is h equal to 2000 over in bracket 11.7 square, and the answer we get 14.61 centimeter. So we get the base length, which is x is 11.70 centimeter, while the side length, which is h, is 14.61 centimeter. C. What is the minimum total cost? To find the minimum total cost, we just need to substitute value of x, which is 11.70, into the cost of the material equation. So, minimum cost equal to 5 in bracket 11.70 square plus 16,000 over 11.70. And the answer we get Rm 2,051 ringgit and 97 cents.
In summary, we were focused on applied maximum and minimum problems, where we use differentiation to solve real-world challenges like maximizing or minimizing. This process enhances our understanding of the practical application of differentiation and enables us to approach optimization problems. By using the technique that I had explained before on how to solve applied maximum and minimum problems, we can effectively apply differentiation to optimize outcomes in various real-world scenarios.